Hello everyone, my name is Sergey Slotin, and before starting the talk itself, I'd like to tell you a little bit about how it came to be in the first place. So, for the last year or so, I've been writing a book called Algorithms for Modern Hardware. I've almost finished it. The printed edition is delayed because people don't like the color of my passport these days, but all its source is hosted on GitHub, and it is freely available online, so check it out if you're interested. The book is about performance engineering, not only designing algorithms that scale and have good asymptotic complexity, like they teach you in colleges, but also about squeezing everything you can out of your hardware. There have already been a few books written on this topic, but mine is different in that it's focused on algorithmic optimizations. I don't just give general advice like try read your data continuously or avoid virtual functions. Instead, I follow a more concrete approach. I do a lot of case studies where I pick some algorithm, like the more simple, the more general, the more popular, the better, and repeatedly ask questions. Why is it taking exactly this time to finish? What's the bottleneck in the computation? Can we remove the bottleneck? And if we can, proceed to remove the bottleneck and go to step 1 until we reach the theoretical performance limit. So for pedagogical reasons, I've looked at a lot of such basic algorithms this way, the ones that are so fundamental that normal, sane people don't even try to optimize. And surprisingly, I've managed to speed up quite a lot of them, and some by a very large margin. One of these case studies, in my opinion, the most interesting and useful because it uses a lot of generally applicable techniques, is binary search, which is what this talk will be about. So our plan for the next 50 or so minutes is the following. First, we will talk about why binary search from the standard library or the binary searches that you might naturally implement yourself might be slow. Then I will tell you how to speed it up using branchless programming, which makes it around 3 times faster on smaller arrays. How to keep this speed up on large arrays by optimizing the memory layout and making better use of your caches. And then how to use simple programming to increase the speed improvement by a whole order of magnitude. The final version of the algorithm will be up to 15 times faster than the standard lower bound. If some of the words I've just said were unfamiliar, don't worry, I will explain them as we go. So, unfortunately, with these increases in performance, the complexity of these algorithms also increases. Not in terms of computational complexity, but the complexity of understanding them. In the book, I needed around 50 pages to cover all of these topics. Today, I only have around 15 minutes. So I will have to omit some details and step up the pace towards the talk. So unless you are a compiler or engineer or a database developer or something, you'll probably not understand all of it. But I hope that regardless of your level, you will be able to learn something new. So let's start by formalizing the problem. We need to implement 2 functions. One of them is called before the benchmark starts, and it performs some linear amount of work with the sorted array. Say it may permute it in some way, or maybe not, maybe it just leaves it as it is. The second one is called repeatedly in loop and benchmarked, and it should do the same thing that the standard lower bound does. It should search for the first element that is greater or equal to a supplied search key. The only difference between this and the standard lower bound is that it returns the value of the lower bound instead of an iterator pointing to it. For the benchmark, we will use random keys and queries, all 32-bit integers, and optimize for the throughput of the lower bound. Also note that this is not technically a drop-in replacement to the standard lower bound, as we are allowed to do some preprocessing before answering the queries. And this preprocessing is not timed. But it is quite hard to come up with a real-world example of when you somehow end up with a sorted array, but can't spend linear time on precomputation. So most of the time, this is a drop-in replacement. Another important distinction is that we only consider comparison-based approaches. So here's an example of an algorithm that does not use comparisons. If we have small keys, say 8 or 16-bit integers, we can just precalculate a relatively small lookup table containing the answer for each possible lower bound query. When the query actually comes, instead of doing any actual work, we will just look it up in this precomputed table and return the answer. When we extend it to larger data types, such as 32-bit integers, the table already requires a ridiculously large amount of memory, but there are hybrid approaches that let you trade off memory consumption for decreased performance. So when you know something about your keys or the distribution of queries, you can and should use methods like that, but we will specifically exclude them from consideration and only look at approaches that use comparisons of their basic operations. And in this model, when we only have comparisons, the standard approach is binary search. We define what's called a search range, which is initially equal to the entire array, And then on each iteration, we pick the middle element out of it and compare it against the search key. If the search key is greater than the middle, the lower bound has to be somewhere to the right of it, and we can only leave the right half of the search interval. Otherwise, the search key is less than the middle, and the answer has to be somewhere to the left, and we only leave the left half of the search range. Either way, the length of the search range on the next iteration will be roughly half of what it was, and after log n iterations, it will fall into a single element that is the lower bound. So STL uses a similar approach, but the standard library needs to be as generic as possible and support not only searching in integer arrays, but also some weird cases such as searching in linked lists of strings or something else comparable. STL uses the start of the search range and the length instead of its first and last element. The start is some abstract forward iterator, the length doesn't even have to be an integer, and the data type is anything that has a comparator. So it is a very generic implementation. If the compiler is set to use the highest level of optimization, both approaches produce roughly the same assembly output. And if you ask any profiler what it thinks about this assembly, it will tell you that it spends most of the time on the instruction that follows a comparison of something from memory with a register value. Something from memory is the middle element of the search range, and something from in register is the search key. So this is not surprising. Here, what takes a long time is not the comparison itself, but the time it takes to fetch the first operand from memory. And this time depends on the size of the array. So here we have a plot of the average time it takes to process one query. We just run a lot of queries in a loop and divide the total running time by the number of queries versus the size of the array. Notice the logarithmic scale. With each division, the array doubles. Theoretically, if all memory accesses had the same cost, the graph would be just a straight line. The algorithm takes log n iterations, and the x scale is logarithmic, so this should be a graph of log n versus log n. However, it is growing faster than linear because as array size increases, it stops fitting into the caches, which are represented here as vertical dotted lines. And the subsequent memory accesses therefore become slower and slower. But let's focus on the left part of the plot for a moment. Here, the entire array fits into the L1 cache, the fastest cache layer. If we take any point on it, for example, this one where the array size is 2 to the 12th, or roughly 4,000 elements, and it takes about 100 nanoseconds to process the entire array. If we interpolate how many CPU cycles are spent on a single iteration of algorithm, we need to divide these 100 nanoseconds by 12, the number of iterations, and multiply by 2 gigahertz, which is the clock frequency of the CPU that we're running the benchmark on. And we get that we are spending about 17 CPU cycles per iteration, which seems too high for the L1 cache. Our entire computation is just a fetch from memory, which takes around 4 cycles on the L1 cache, a comparison, and some simple arithmetic with the search range boundaries, which cumulatively should take another 2 or 3 cycles. So this should all be like 2 to 3 times faster than what we've measured. And to understand what's happening here, we need to know about one interesting feature of modern CPUs. So to execute any instruction, the processor needs to do a lot of preparatory work first. It needs to fetch a block of machine code from memory, it needs to analyze it and understand which instructions are there, execute these instructions, possibly involving some operations from memory, and write the result back into registers so that they can be fed into the next instructions. Each of these operations has some intermediate steps, and in total, from start to end, the whole process takes about 15 to 20 CPU cycles from start to finish. In order to not wait these 20 cycles on each instruction, modern CPUs use an optimization called pipelining. So the idea is that when an instruction finishes its execution on a certain stage, the model responsible for the stage can start processing the next instruction right away, without waiting for the previous one to fully complete. This way, instruction processing and execution can overlap in time, and in this approach, we increase the utilization of the CPU and the throughput of the entire computation. This approach does not reduce actual latency, but it gives the programmer an impression that it consists only of the execution and memory stages. Pipelining has a drawback in that if an instruction for whatever reason can start executing on its designated clock cycle, the next instruction that depends on it has to wait. and also the next one and the next and so on, causing what's called a bubble that propagates down the pipeline and causes inefficiency. The reasons for these pipeline stalls are called hazards, and there are several ways they can occur. First, there are structural hazards, which is when there are two or more instructions that need the same part of the CPU at the same time. So, for example, if there is some execution unit for multiplying numbers, and there are two instructions that need to multiply numbers, one of them has to wait. The second data hazard occurs when one instruction needs for some other to complete first, because there is a logical dependency between the two. Like, for example, say if the output of one is used as one of the other's operands. So, for example, in binary search, there is a dependency between iterations. We can't start executing the next iteration before the previous one completes, because we need to know what element to fetch and compare against on the next iteration, which is the output of the previous iteration. And the last type is control hazard, and it is when the CPU can't tell which instructions to execute next. And this type of hazard is especially interesting to us because the bubble emerges at the very beginning of the pipeline, and we need to wait entire 20 cycles to refill the pipeline back. So it occurs due to branching, due to some type of branching. For example, if you have an if statement in your code, where depending on some condition, you execute either one stream of instructions or the other. Spending entire 20 cycles on each if statement is pretty unpleasant, so both hardware and software people have come up with ways to mitigate control hazards. First, modern CPUs use what's called speculation. The processor tries to actively predict which branch is more likely to be taken. It does so using statistical methods and starts executing the branch ahead of time. If the predicted branch was the right one, everything is good and you do not need to stop the pipeline at all. And if the branch was mispredicted, and only in this case, you need to pay these 20 cycles to fill the pipeline back up again. So branch prediction works at least half of the time because it's hard to do worse than with a coin toss. But in practice, it is usually much better because branch predictors are pretty sophisticated nowadays. Some use simple hardware neural networks that are dynamically updated and can detect many simple patterns. And the second approach is the software one, which is just to remove the branches altogether. And this is called branchless programming. So in this context, let's try to look at our binary search. It has two branches. One of them is the loop condition. On each iteration, we check if we are done, if the search range has compacted into a single element or not. This branch is not really dangerous. Thanks to branch prediction, most of the time the CPU will be able to successfully tell if we are done or not. Say if we have an array of 1 million elements, then we will be doing either 20 or 21 iteration. The processor will be able to predict the first 20 of them, and maybe we'll fail on the 21st one. But this only happens once every 20 iterations, so it doesn't really factor in that much. The second branch is inside the loop body, and it depends on the result of the comparison. And unfortunately, we cannot predict this result better than with a coin toss, because in our benchmark, all queries are random. So we need to find a way to get rid of it. And to get rid of this branch, we will need to adopt the approach used by the standard library. Instead of the left and right boundaries, we will maintain the beginning of the search range and its length. It seems like we will just make things worse. Just visually, this implementation is one line longer, but it will become clear why we did that. So the general approach to removing branches is to make it so that fewer variables depend on the condition. Here we have two variables that depend on the outcome of this comparison. First, we have the base variable, which we either move to the middle of the search range or leave it as it were. It is a fundamental dependency, and there is nothing we can do about it. And apart from that, we also have the length of the next search range, and it doesn't depend on the comparison that much. So it's half of the previous length, but either sealed if we go right or float if we need to go left. Half of the time, the search range length is even, so it doesn't even matter. This seems like a very minor distinction, so let's make it so that it is always sealed, even if we go left. This is still correct, because we are only maybe extending the search range one element to the right, and it doesn't change much in terms of correctness. This lets us move the length recomputation out of the body of the if, with the only downside that we will maybe do slightly more comparisons on average. Also, because we compare slightly different elements, this algorithm is not strictly equivalent to the standard binary search, although it still has the same log n upper bound on the number of comparisons. In fact, these extra comparisons have an upside. We will always be doing exactly log n rounded up iterations, which makes the last branch, the loop condition, perfectly predictable. So there won't be any branch mispredictions at all. Now that our computation is so simple, we can replace this branch with this arithmetic trick that optimizing compilers replace with a special conditional move or cmove instruction that assigns a register to either one value or the other, depending on the condition. For example, depending on how this comparison goes, it can assign the variable base to either base plus half or base the way it was. So if we run our benchmarks again, we can see that for small arrays, the performance increased by a factor of 2 to 3. But on large arrays, the performance degraded. Why might that be? The thing is, when there is branching, the processor tries to predict the more likely branch and starts speculatively executing. Even if the prediction can be done better than with a coin toss, in these 50% of cases when it does work, the CPU will perform usable work. It may prefetch the element that we will compare against on the next iteration, and thus reduce the latency of that iteration. And when the array is large, the memory efficiency far outweighs the benefits of not having branches. A branch misprediction costs about a dozen cycles, and a fetch from the main memory costs about 100 cycles, so these are not comparable numbers. So the normal branchy binary search has this free prefetching mechanism. While in the branches binary search, there are no branches, no speculation, and hence no prefetching. So to even the playing field, we cannot explicit prefetching to the branches binary search. And compilers have a special intrinsic for doing that. In GCC and Clang, there is this built-in prefetching index that takes the address of an element to prefetch, and it loads its entire cache line into the L1 cache, so that the next access to it is fast. We can use it to prefetch the elements that we may compare against on the next iteration. That is the middle of the left half and the middle of the right half. So if we do that, we will improve the performance on large arrays, but slightly degrade the performance on smaller arrays because we still need to perform these two prefetch instructions on each iteration. We could continue doing this and prefetch, say, 2 iterations ahead. We would need 4 prefetch instructions for that, one for each of the 4 quarters. The search range could be split into iterations. And then the right part of the graph will continue to go down, but the left part will continue to go up. So there is a natural trade-off here. But if we started talking about memory and the right part of this graph, let's discuss cache efficiency and of the binary search. So the standard binary search uses cache with 2 mechanisms. So the first one uses the fact that the first dozen or so iterations, we are fetching the same elements over and over again. So they are likely to be cached. For example, the first element that we compare against is always the middle of the entire array. And on the second iteration, we only compare against 2 elements, the middle of the left half and the middle of the right half, and so on. This number grows, but the set of elements that we need to fetch on the first few iterations is very limited. And if the queries are random, then between the time we fetch the first an element for the first time and fetch it again, it is very unlikely that we will kick it out of the cache with some other requests. And if the queries are not random, the situation is even better. So the second mechanism relies on the fact that the memory is split into blocks of 64 bytes, also called cache lines, and the memory system works with these 64 chunks of data instead of individual bytes. So when you fetch 1 byte, any byte from the memory, you also fetch its 63 cache line neighbors, whether you want them or not. That's just how memory works. So having this in mind, the last 5 or so requests will probably span only just 1 or 2 cache lines, because the search range has already been compacted a lot and all queries are local. So when we fetch the first of any of these elements, we will fetch its entire cache line, and its cache line will be kept in the L1 cache, so the next accesses will be free for us. So binary search actually works surprisingly well, memory-wise. If we were to read just log n completely random elements of the array in each iteration, it would work around 5 times slower. because basically each fetch would come from the main memory. But using this mechanism, we can cache the first and the last few requests, which is very beneficial. So the only thing that we can optimize here is this consideration. We group hot and cold elements together. So that is, the elements that we read very frequently occupy the same cache lines with the elements that are never read. So, for example, we compare against the middle element each time on the first iteration, and so it is definitely in the L1 cache because we fetch it so often. The element right after it is very likely to be in the same cache line with it, but we almost never fetch it specifically. So to compare against this element, we need to search specifically for it, which happens with a very low probability. But these two elements, the middle and the next one, probably share the same cache line because they're close in the address space. So we have to put them together in the same cache line in the L1 cache, which is a waste of space. Instead of that second element, we could have put some other element that is accessed more frequently. So ideally, we want to change the layout in a way that would group hot elements with hot elements and cold elements with cold elements. And to achieve this, we need to permute the array elements in an optimal way. And the permutation that achieves that is actually known to humanity for quite a long time. So in 16th century Austria, there was a nobleman named Michael Eitzinger. He is known for his work on genealogy, in particular for his ancestor number system known as Ahnentafel, which is German for ancestor table. Ahnentafel works this way. The subject of Ahnentafel, in this case, is Henry III, a 16th century French king, is listed as number 1. And then recursively for each person numbered k, their father is listed number 2k, and their mother is listed number 2k plus 1. For example, Henry II, the father of Henry III, is assigned number 2. His mother is assigned number 3. His paternal grandfather, Francis I, is assigned number 5, and so on. In this numeration, each ancestor gets a number, although some ancestor might get more than one. So, for example, here, Francis I, or ancestor number 4, the grandfather, inherited the crown by marrying a daughter of his cousin, ancestor number 10, Louis XII, who didn't have a male heir. This is 16th century France. So if you continue this table just one generation further, there would already be some data redundancy. But in general, this numeration is very compact, and it lets you store all that pedigree data and search it without drawing diagrams and waste too much paper. But apart from being compact, this system has many other cool properties, and for these properties it has been widely used in computer science in relation to binary heaps, segment trees, and other binary tree-like structures. By using this numeration for storing nodes, you can store the entire tree implicitly and not waste memory on pointers between nodes. So if we make a balanced binary tree out of a sorted array, and then apply this Eitzinger numeration to its nodes and write all the values of the array according to their numbers, we get just the layout we need. Notice that the elements will be sorted by their distance from the root, and so hot elements will be grouped with hot elements, and cold elements will be grouped with cold elements, sorted by their frequency of their accesses. So the temporal locality of this layout should be much better. So to build this permutation, we can write this elegant recursive function, the correctness of which I'm not going to prove because this is not important. Just believe me that this recursive function works, and it works in linear time. The interesting part is how to perform search in this array. We need to start with the first element, k equals 1, and then until we reach a list, we compare against the current element that k points to. Depending on how the comparison went, we either go left to node number 2k or right to node number 2k plus 1, which can be implemented with this cute arithmetic trick that will also be branchless, by the way. So descending the tree is simple as fast, but the problem is you need to restore the lower bound itself in the end. In normal binary search, we just maintain the tree as the search range explicitly, and when it contracts to a single element, we just immediately know where the lower bound is. But here, the resulting index k does not necessarily point to the lower bound. So here's an example. Here we have a 10-element array of numbers between 0 to 9 inclusive. and we are searching for the lower bound of 3. On the first iteration, we will compare against the first element, 6, and 6 is greater or equal to 3. So we go left, multiplying k by 2. On the second iteration, as k equals 2, we will compare against the second element, 3. And as 3 is also greater or equal to 3, we will once again go left and multiply by k by 2. Next, we will compare against the fourth element, 1. And it is less than 3, so we go right this time, multiplying k by 2 and adding 1. And now we point to element 9, ninth element, second to last, which is 2. And 2 is again less than 3, and we multiply k by 2 and add 1, and end up with k equals 19, which is not even a valid array index. So k does not point to the lower bound, but we can still use it to restore the position of the lower bound. To do this, we need to use the fact that in this search, and in comparison-based search in general, we will compare against the lower bound at some point, and after that, since we just compared against the lower bound, we will go left once, and then, since we have compared against the lower bound and everything in our search range is now less than the search key, we will be comparing against lesser elements and keep going right until we reach a leaf. So, when we compare against the lower bound, we will go left once and then keep going right. To find the lower bound itself, we can look at k and use its binary representation to restore the index of the lower bound. To do this, we need to know that when we go left, we multiply k by 2, which is equivalent to adding a 0 to the end of its binary representation. And when we go right, we multiply k by 2 and add 1, which is equivalent to adding 1 to the end of its binary representation. So all left turns will correspond to 0 bits, and all right turns will correspond to 1 bits in the binary representation of k. So to find the lower bound itself, we need to cancel the longest suffix of the last right turns, which is equivalent to cancelling the longest suffix of 1s and in the binary representations of k. So, on modern CPUs, this problem of cancelling the largest suffix of 1s can be done with a special CTZ instruction, which stands for count trailing zeros, and it does exactly that, counts the number of trailing zeros in the binary representation of a number. It is exposed in compilers as there is built-in FFS intrinsic where FFS stands for find first set bit, which is the same as the number of trailing zeros. So since we need to cancel the longest suffix of 1 bits in k, we can negate its bits and then call this find first set intrinsic, which tells us the number of zeros in the inverted number, which is the same as the number of trailing ones in the original number k. And then we just shift k by exactly that amount. So this entire 3-minute discussion just falls into this one line of code that executes 3 one-cycle instructions. So if we run our benchmarks again, it's actually not looking good. On small arrays, the performance is roughly on par with branchless binary search because our computation is simple and it doesn't require branches. But on large arrays, it is even worse than branchless binary search. This happens because we no longer have the second type of cache sharing. We are jumping in increased steps, and the last few requests are not in the same cache line anymore. Also, another minor issue is that the number of iterations is now not constant, as it was in the branchless binary search. This makes the main loop branch unpredictable unless the array size is a power of 2 or some number that's close to it. You can observe it if you zoom into that bumpy part of the graph on the left, where the array is still small enough for this effect to be very visible. There are these bumps that repeat every time the array size doubles, and they are there because the CPU can predict if the number of iterations is log n rounded up or log n rounded down. So this is bad. We've spent so much time, and our algorithm is strictly worse than the branchless binary search. But we still have not tried prefetching yet, so let's add prefetching. So if we try to do it naively, then we will need to analogously insert two prefetch instructions where we fetch the left child indexed to k and the right child indexed to k plus 1. But we can notice that these elements will be very close together in the address space. They're literally the neighboring elements in the array. So they're very likely to be in the same cache line, and so we can just fetch one and the other will likely to be prefetched too. So we basically can do two prefetches at the cost of one this way. Continuing this logic, if in 2 iterations we will be comparing against some element between 2k and 2k plus 3 inclusive. They are also very close in the address space, so we can fetch all of them with just one prefetch instruction. And continuing this logic, we can fetch element index 16k. That is the element that we would need in 4 iterations if we went left in all of the next 4 comparisons. And we will also fetch its next 15 neighbors. To ensure that we fetch all of them, we can allocate the array itself on the beginning of a cache line. And then, if we are fetching element index 60k, its memory address will be divisible by 64, because the address of the array itself is divisible by 64, and we are shifting it by some whole number k times 16 times 4, because we are indexing an array of integers. So the address of the element that we are prefetching will be divisible by 64 and will begin on some cache line, and the next 15 elements will be on the same cache line with it. So with this one prefetch instruction, we are fetching 16 elements, all of which will be just the ones that we will need in 4 iterations. So on each iteration, we will use just this one prefetch to get all 16 elements that we may need to compare against in 4 iterations. And when we will be actually comparing against an element, we will have started prefetching it 4 iterations prior to that. So when we run the benchmark, this correspondingly speeds up the algorithm by a factor of 4, and about 2 times faster than the standard binary search. There is, however, one drawback. During each iteration, we will be essentially fetching 4 cache lines concurrently, and we will consume more memory bandwidth this way. If the memory bandwidth is some limited resource, for example, if we are running this code on some database where we have 20 CPUs, CPU cores, and just 1 stick of RAM, it will quickly become the bottleneck. So instead of trading bandwidth for latency this way and fetching 4 cache lines in parallel, we can actually fetch 4 times fewer cache lines and make this speed up independent of bandwidth. But to do that, we need to once again change the memory layout. So instead of binary trees, we will switch to a layout inspired by Bitrees. A Btree is a generalization of a binary tree. In its nodes, there are up to b keys that distinguish between b+1 children. The keys within a node are sorted, and a child's sub-tree keys all need to be between the 2 corresponding keys in its parent. When b equals 1, a Btree becomes just a binary tree. So to perform search in a Btree, we need to similarly start at the root node and find the first key in that node that is greater or equal to the search key. And that gives us the pointer to the only child node that might contain the lower bound. And we need to go to the child and continue the search until we reach the leaf. Somewhere on the path, we have to compare against the actual lower bound, and we keep track of it and return it at the very end. This approach reduces the tree height and thus the number of iterations, but we also have to perform more comparisons in each node that we visit. In terms of the pure number of comparisons, this approach is actually not beneficial. We will do more comparisons than we do with the standard binary search. But as we've seen before, the number of comparisons is not exactly the metric that we want to minimize. What we really want to optimize is the number of cache line fetches, and Btree lets us do exactly that. So to minimize the number of cache line reads, we will set b, the node size, so that a node fully occupies a single cache line. In our case, we set b to 16 because this is how many integers fit in a single 64-byte cache line. Before, the height of the tree was log n base 2, and now it is log n base 17, because that's a new branching factor, which reduces the tree height more than 4 times. If the height is lower, we will need fewer iterations, and we will need to fetch fewer total cache lines. So, to not waste precious CPU cycles and cache space and pointers, we can make a Btree implicit by generalizing the Ancestor numeration. We can say that the node is numbered 0, and that a node k has 17 children numbered from 17k plus 1 to 17k plus 17. If b equals 1, this turns into the Ancestor numeration, with the exception that the root node is numbered 0 and not 1. So we start from 0. To abstract away from the details of how this structure is stored in memory, we can allocate it as a simple 2-dimensional array with dimensions of the number of nodes times the size of a node. And then we define a function named go, which takes the number of a node and the index of a child, the local index of a child between 0 and 17, and returns the number of the child node using this formula we defined. We can build the structure similarly to how we did it for the Eitzinger binary search, but I will also not stop here because this part is not interesting. The interesting part is performing the search in the structure, and for this we need to be able to find the local lower bound in a node. That is, find the index of the first element that is greater or equal to the search key. The most straightforward way to do this is with linear search. We just check each element from left to right in a loop and return the first one that is greater or equal to the search key. Assuming that all keys and queries are random, this approach takes about b-half comparisons on average. Also, there will probably be one branch misprediction because the processor can't tell in advance which of these elements will be the first match and on which iterations we will exit the loop. To get rid of the branch misprediction, we can instead calculate a mask containing ones for all keys that of the node that are greater or equal to the search key. Then we can call the already familiar find first set intrinsic on this mask, which will give us the position of the first of the lowest set bit, which is the same as the index of the element that is greater or equal. This way we can get rid of all the branching. The compiler will just unroll this loop as 16 iterations of this bit trickery. But we also need to perform more comparison this way. In the previous approach, we performed b-half comparisons on average due to probabilistic reasons, and here we are making all b comparisons all the time. So overall, this approach is not beneficial, but here we can use SIMD instructions to speed it up. So SIMD is an acronym for single instruction multiple data, and it is a general approach in computer engineering where some operation is applied to a whole block of data instead of a single scalar data point. On modern CPUs, SIMD is represented with vector instructions and special wide vector registers capable of holding a block of data. In our problem, we can use SIMD instructions to load a block of node keys and use a single vector instruction to compare it against the search key and get this large vector mask where ones correspond to elements that are greater or equal to the search key. Then we can use the special move mask instruction that takes this large vector mask and makes a small scalar mask out of it. And then we can call the already familiar find first set instruction to find the needed index, just as we did before. The CPU that we optimize for supports a SIMD extension called AVX2, which has 226-bit wide registers that can fit 8 integers. We can write a small function that takes a vector of 8 copies of the search key and a pointer to a memory block that has 8 node keys. It loads these 8 keys in a vector registers, does the comparison against the search key, and produces an 8-bit mask with this move mask instruction out of this vector mask. So it's just 3 instructions for 8 comparisons, which is a pretty good ratio. This function does 8 comparisons at a time, but we have 16 elements in node because we chose it so that is the size of the cache line. So to find the local lower bound in the whole node, we can call this vector procedure from the first part of the node on the second half of the node, get 2 8-bit masks, combine them together into a single 16-bit mask, and then use the find first set instruction on this combined mask to get the index of the needed element and the index of the child that we need to descend into. Now what is left is to glue it all together. To perform the tree search itself, we need to start from the root node, and then until we reach a leaf, we need to find the local lower bound in the current node, which gives us the index of the child that we need to that might contain the final answer, and we need to descend into that child and continue. In the end, we will arrive to some leaf node, but that leaf node does not necessarily contain the global lower bound, the actual answer to the query. This problem is similar to the Eitzinger binary search, if you recall. But we meet the global lower bound somewhere on the path to that leaf node. So to solve this problem, we can just keep track of the answer and update it on each time we descend down the tree, if the node had a local lower bound here. So if we run this benchmark again, we get another 50% speed up over the Eitzinger binary search. By the way, Edward McCrae and co-inventor of Btrees once said that the more you think about what B in Bitrees means, the better you understand Bitrees. It can stand for balanced, blocked, broad, bushy, or also the name of the other co-inventor was Rudolf Baer, and they worked for Boeing Research Labs at the time, and so on. So you know, this is a fitting name for the data structure. And so by analogy, I call this particular modification S3 because it is static, it's succinct, it's small, it's speedy, it uses simd, and so on. But this is just a little remark about naming. Let's get back to performance. So this structure can actually be optimized by another 20% or so. But further optimizations run into restrictions regarding the memory layout. So here we have two fundamental problems. First, on each iteration, we need to update the answer despite the fact that most of the time the global lower bound, the final answer, will be just in the last node, and we can just read it from there. But we still need to do that because there is 1 in 17 chance that it is not there. Second, the depth of the leaf nodes of the tree is not uniform. So while descending, we perform a non-constant number of iterations, and this may cause one branchless prediction at the very end. It is just a single branchless prediction, but we ideally would like to avoid it. We can solve both of the problems if we modify our layout a little bit. Instead of Btrees, we will use a layout based on B+ trees. This is a modification of a Btree that is actually more popular than the original Btree. When people say Bitrees, they actually mean B+ trees. B+ trees differentiate between internal nodes and data nodes. Internal nodes store keys and pointers like in Bitrees, and data nodes only store keys and optionally the pointer to the next data node. Also, all keys are copied to the higher layers, so there is some data redundancy, and the structure is no longer succinct. So, for example, if the branching factor is 17, we need around 6% more memory to store the internal nodes that contain the copies of the keys of the data nodes. Data nodes form the last layer of the tree, and since it contains all the data and all leaf nodes have pointers to the next leaf node, you can easily iterate this tree. You just jump somewhere, and then you read the needed suffix of the current node, and then you follow a pointer to the next data node and continue. This is why B+ trees are so popular. This access pattern is very common in databases where you need to return not just one object, but a whole range of objects sorted by some key. It is quite a bit harder to build this tree, but it simplifies the search procedure and actually solves both of our performance problems. So first, we no longer need to perform answer updates on each iteration, because all keys are present on the last layer, and we can just read the final answer from the last node. Second, B+ trees grow upwards. This is just a fact. They need to grow upwards because a data node can turn into an internal node. This means that the depth of each leaf node is uniform, and we will be performing a constant number of iterations. In fact, in this, if the size of the tree is a compile time constant, the height of the tree and consequently the number of iterations, uppercase letter H in the code, will be a compile time constant too. So the compiler will be able to unroll this loop into just a fixed number of iterations. So there will be no branches at all. It doesn't matter predictable at all, just no branches, and this means no branch mispredictions. And also, this is more of a functional requirement than a performance issue. We can now easily return the index of the lower bound and not just its value, which is needed in some application. We can do this because the data layer, the last layer, contains all keys in their sorted order. And to get the index of an element in the original sorted array, that is the number of elements that are strictly less than the lower bound, we can just subtract the beginning of that last layer from the index of the lower bound in the tree. We couldn't do that with all the previous approaches because we applied some weird permutation to the array, and so restoring the original index of an element is a non-trivial problem. But here we can do it very easily. Also, for the same reason, we can reuse the original sorted array as the last layer of the tree, and we can only build these internal nodes that take 6% of the memory. So if we for some reason need to retain the original sorted array, we can just waste 6% of its memory on this fast index computation. But the main benefit is performance, and if we switch to this approach, we make the algorithm around 50% faster on large arrays and 2 to 3 times faster for smaller arrays. All the performance improvements I've been talking about in the last 20 minutes were multiplicative, and after compounding, they yield a very impressive improvement compared to the standard textbook binary search that we started with. If we look at the relative speedup, our final solution works up to 15 times faster on smaller arrays and around 7 times faster on larger arrays. But there are actually many tiny things that, in my opinion, can be still improved. So, for example, here on the left part of the plot, you can see very distinctive sawteeth. This happened because the performance of our final algorithm grows like a step function. So in certain intervals, the tree grows uniformly for all nodes, and we perform exactly one more iteration as we did before. And for arrays fitting in the lower layers of cache, the number of iterations is all that matters. Meanwhile, the standard binary search performs a non-constant number of iterations that grows smoothly. If you divide one graph by the other, you get these sawteeth. To fix this, we can make the node sizes of each layer non-uniform to delay or speed up the tree growth, adaptively depending on the tree size. Say, we can make the root node only contain 8 elements, or make the last layer nodes contain 32 elements each. This should make the graph look more like its upper envelope if we do it adaptively for different array sizes. Apart from that, we can also try other layer modifications. For example, we can do what's called hierarchical blocking, which is to group 2 or more layers together so that a node and its children are closer in memory. And this locality can be beneficial because, for example, this way we also fetch fewer memory pages. We can also try to add prefetching. We obviously can't prefetch all 17 child nodes. This is unfeasible, but we can fetch some of them on lower layers, and it will work at least part of the time. We can also use what's called non-temporal memory accesses. This is when we fetch a cache line but do not keep it in cache or keep it at a specific layer of cache instead of on one. This is beneficial when we know that we will not be using that data again later, and we can use that cache space for something else. So in our case, we can use these non-temporal reads for the last layer so that they do not kick out the internal nodes from the previous layer out of the cache. We can also try and experiment with different comparison kernels, which is especially important if we consider the other block sizes and also other seamed extensions. The optimal kernels will probably be a bit different for AVX 512 and ARM Neon, for example. Also, to make a practical library, we need to generalize to other data types other than integers. This can all be easily ported to other numerical data types, such as floats, or maybe pairs, or short tuples of integers, and also some use cases involving short strings, such as country codes or stock tickers. But in general, the data type might not be so easily comparable with SIMD. All the considerations regarding branchless programming and cache efficiency and stuff still apply, but without SIMD, the speed up will not be so massive. So this is sort of a call to action to the C++ community. There is still a lot of work to be done that I cannot do it alone, both in terms of further optimizations. I wouldn't be surprised to see this algorithm optimized by another 20 to 30% for 20 times total speedup. But more importantly, in terms of usability in libraries and portability to other platforms. I'm getting pingbacks from various people who adapt their projects using some of these ideas, but there are still no production-ready standalone implementations yet. And my own code is just a proof of concept. But if some excellent C++ programmer gets as excited about binary search as I am, this can all become a reality. And also, we can expand the scope and consider not only searching in sorted arrays, but also extend to dynamic search trees and other similar tree-like structures such as heaps. I tried this with Bitrees, dynamic Bitrees that is, that need to support insertions as well as searches. I also use a B+tree inspired approach, but I needed to tweak it a little bit, so I call this modification B-tree, which is a very confusing name because people don't notice the space between the minus and the tree and think it's just Btree with a hyphen. But anyway, to adapt the algorithm to the problem, you basically need to store explicit pointers next to keys in internal nodes and use these pointers instead of indices when descending down the tree. This is essentially the only line of code that needs to be changed in the entire search procedure, although the insertion procedure becomes much more complicated than that. So since we need to support both insertions and searches, our optimization problem becomes two-dimensional, and there are trade-offs between the two. I compare it against the standard set, which is internally implemented as a red-black tree, and also against the Btree from Google's upsale library. And against the standard set, the B-tree is 10 to 15 times faster for insertions, and against upsale's Btree, we are 3 to 7 times faster depending on the dataset size. The code I wrote to support insertions is not very well optimized yet, so the speed up here is only 50% or so, but I believe it can be improved to almost the speed of the search. This is also, again, just a proof of concept. There are other operations that a proper search tree needs to support, such as deletion of nodes and iteration, but I'm very certain that with some effort they can be implemented and with similar performance improvements. So that's about it. As I said at the beginning, I had to skip some details, so check the article and the code if you're interested. Thank you, everyone, and I'm happy to answer any of your questions. So first question, is there any reason why you're using int or unsigned for addressing instead of size t or pointer diff t on 64 bits? No, there is no reason. I just use these types for simplicity. The right way to do it, the C++ way to do it is to use size t types for these offsets. This also allows you to use a 64 to work with more than 32 2 to the 30 second power size of the array. What about memory consumption? Yeah, so all the approaches except for the last one use linear memory. So essentially, the first, the branchless binary search, it doesn't need to permute the array in any way. So it can actually be used as a drop-in replacement and can use just the array that you supplied. The other arrays need to perform a permutation of its elements and use the same number of memory. If you need to retain the original sorted array, this means you need to copy the array and then permute it. So there will be a 2n memory consumption. The S+3, the one that copies keys to upper levels, it uses some more memory. As I said, it uses with branching factor of 17 around 6% more memory, but it has this upside that if you need to retain the original sorted array, you can reuse it as I said in the talk as the last layer in the tree, and only spend this 6% of memory on this index part on the internal nodes in the S+3. Also, the memory consumption, if this question is about the dynamic problem, is about Bitrees, so you need to store the keys and also the pointers. The pointers, you can store it as pointers themselves, or you can store them as indices. In the code, I'm storing them as indices so that they are easier to fetch. An index is a simple int, so it takes 4 bytes, and a pointer on 64-bit machines takes 8 bytes. So I'm using indices to optimize cache utilization. And apart from that, Bitrees have a problem that not all nodes are fully filled. So on average, they will be about 2/3 full. So you will need about 1/3 more memory for the last data layer where all the keys are stored, and also some memory, not very significant amount of memory for the internal nodes. So essentially the memory overhead of the last tree is about 30%, which is really great, which is better than what upscale does and better what the standard set does, because the standard set uses pointers for each element and also some, I guess, helper variables in each node. Because it's a red-black tree, it needs to store its color. It also probably needs some padding or something like that. So it's much better compared to the standard set, especially. Do you benchmark include preprocessing as well, or just the lookup? The benchmark include only lookup, but well, I sort of talked about it at the beginning. There are very few problems where you cannot afford, where you get a sorted array in some way, but cannot afford a linear time to do some precomputation with it. But this part of the computation is actually really fast. It's much faster than sorting, of course. And I think the last time I measured it to actually figure out if this is an issue or not, for the Isenglass array, which has a pretty expensive permutation because it uses recursion and stuff, the time it takes to build a 1,000,000 element array to do this permutation, which is not very optimized, by the way, is about 100 times fewer than the time it takes to perform 1,000,000 searches on this array data. So the cost per element is about 1/100th of a single query. So the preprocessing is very fast, and in my code it's not optimized yet, but it can be still improved. So in most of the use cases, this is not a major concern. How much of the speedup depends on the memory instructions being applied to ints? What slowdown would you expect looking up floats or even doubles? Yeah, in this algorithm, it doesn't matter. For all numeric types, this can be very easily extended. So there are, I mean, if you're doing it for floats, floats are also occupy 32 bits of memory, and they're fetched exactly the same way as the ints are fetched. You essentially will only be using different instructions for comparisons, and that's pretty much it. So for larger data types, you would probably need to use smaller node sizes in the last approaches. That will increase the tree height and the number of memory fetches. So, for example, if you're doing this for 64-bit integers or doubles, you would need twice as much memory, and to process them to do the comparisons, you would compare four doubles at a time. So there would be a slight slowdown here. I guess you would use a branching factor of 9 instead of branching factor of 16. So this would make the tree like 20% larger or so. So the slowdown will be 20% for larger data types, but it would also speed up computation for smaller data types, such as short integers or maybe characters. I don't know why you would do binary search in an array of characters, but if you do this, this speed up would be more by another 20 or 30%. Yeah. I guess there are no other questions. So thank you, everyone. And I guess this is it.